This is a video for the STEM students. It goes into depth in some of the stuff we kind of glossed over back a few chapters ago when it came to angle side side. As you recall, with angle side side stuff, we couldn't say that, triangles were congruent, with the one exception of hypotenuse leg. But now we're going to touch on that again. We're going to call it SSA though, just to be appropriate. So when we have a triangle with known information being the side, another side, and then another angle where that angle is not included, we actually can make some conclusions, and we're going to figure out what those conclusions are, and we can figure out what possible options there could be for triangles, where before we just said, oh, we can't be too sure, so we'll just not try all. So if we have a known angle, so we'll call that angle A here, and we have side B and then side A as known lengths, we have a couple different options. The first is where side A is just fact, it's so short, it's shorter than side B, it's shorter than the hypotenuse, or not the hypotenuse, the altitude or the height here, at which point it doesn't make a triangle. The other option is where that length of side A is equal to the height. If it's equal to the height, then it connects here and it forms a 90-degree angle, and there's only one possible triangle that forms this. And so this is how we're able to use the hypotenuse leg triangle congruence theorem, is because there's only one possible triangle when we have this situation. Another situation is where our side A is greater than the altitude or greater than the height, but it's still less than side B. And at which point it could connect at basically two different points, and we could have two different sized triangles and two different shapes of triangles as well. So this is the main reason why we weren't able to do any sort of congruence theorem using angle side side. And then finally, if our side A here is really long, and it's much longer than side B, then it can't make an angle over here, but it can form a triangle by connecting away over here. So there's one possible triangle. I'll show you, I made a little GeoGebra for this. Let's show it to you guys. So we have one here. This is just our first example where we have this short little side A. It doesn't make a triangle no matter what we do with it, right? Here's our example for the second one. As it comes in, it goes zoop, and it just perfectly touches that side, and we can form a 90-degree angle, and that's the only possible triangle we can make, right? For this guy here, it touches it not only out here, right? We can make a triangle there, but we can also make a triangle like here. So this guy has two options. And then finally, this one's really long. See, so over here, it doesn't make any triangle at all. And then it finally connects into a triangle by coming over here. So there's one possible triangle for that guy. So that's just so you can see that visually. And the reason why we're covering this is because we'll need to check and see if triangles are even possible, and if they are, how many types of triangles. And once we figure out how many types of triangles are possible, we can actually conclude, using some of our trig, what the missing side lengths and angles will be. So here's our example. It's this airplane wing, but the only thing you really need to know is that we have a known angle and a known side and another known side. So our angle here is 30 degrees, angle A. Side B here is 18 inches, and so we're going to go ahead and put that in the figure. Why aren't we going to put this side A in the figure? Well, we basically don't know what it's going to look like. I don't know if it's going to be like an acute triangle or an obtuse triangle, or like what these angles are going to be. So we want to try and figure that out. But we do know that side A is 15 inches. So our first step is to determine what types of triangles are possible. How many are there? What's it going to be like? So in order to do that, we need to find the altitude, or the height of the triangle. And as you recall, the height is just the distance to point C, or this, we can find different heights, but in this case, the altitude we want is the one that connects the altitude of the vertice that is between the two known sides. So in this case, it's point C, which means it'll be perpendicular to side, what is this, side C here. And so we're basically going to put this label this as H. We need to calculate H. Note here, it makes a right triangle. So we can set up our formula here. The sine of 30 degrees is equal to H over 18, and then solve for H. Some of you other astute guys may have noticed it's a 30, 60, 90 triangle. So therefore H is just half of 18 or 9. So because the height or the altitude of that triangle is 9, the height of that triangle is 9, what can we conclude about the number of triangles we can make? We know that A is 15. Right? So we go back here and we say, okay, is A less than 9? No. Is 15 equal to 9? No. Is A greater than B? Well, A is 15, B is 18, so no. Is A less than B and greater than the height? Yes. So that means we're going to have two triangles. So we're going to have two possible triangles, and we're going to draw them. So this is what they look like. They both have 30-degree angle, then an 18-inch side, then a 15-inch side, 30-degree angle, 18-inch side, 15-inch side, but they look very different, right? Our next step is to calculate the three things that will be different, right? There's three things that are totally the same, and the three things that are different are angle B, side C, and angle C. So the first step is to calculate what angle B is. So we need to calculate this angle. And there's a couple ways to do it. The way the book sets it up is they basically use law of sines. And they say that of angle A, which is a known, over this known side, right, is equal to the sine of angle B over this known side, right? So that gives us this formula. It says that the sine of angle B equals this thing. And we can solve for B using the inverse sine, but we have to be careful here. This is the first time where we're using inverse sine where one of our answers, right, could possibly be greater than 90 degrees. And in fact, for your calculator, it will never give you an answer for the inverse sine that is greater than 90 degrees. And the reason for that is it basically is assuming that that you're using it for our right triangle purposes. And in our right triangle, neither of the two other angles are greater than 90 degrees. But in this case, it is possible for it to be greater than 90 degrees. So I'll show you how to calculate. The first one is the acute angle, right? So this is our acute angle B. And this is one is less than 90 degrees, and this is what we're essentially solving for. So when we plug this into our calculator, we take the inverse sine of this thing, and it spits out 36.9 degrees. So we know that angle B here is 36.9 degrees. The other possible angle that would that could give us this value here when you take the sine is going to be greater than 90 degrees. And we can kind of see it here. If we go up to these triangles here, we have this blue triangle, right? It has a hypotenuse of 15. It has this height. Has a 90-degree angle. We know that these two triangles are congruent using hypotenuse leg, right? We know that this angle is 36.9. Therefore, this angle is 36.9. And we know that since this is a straight line, that angle B2 and 36.9 are supplementary. So to find angle B2, we can simply subtract it from 180, right? And this may not be super satisfying for you guys. Another way to think of it is, remember when you graphed sine on the coordinate plane? It looks something like this. It goes, let's see, it goes like up and down and up and down. Okay, it's not the most beautiful one, but it gives you an idea. Essentially, it's the inverse the sine of, you graph the sine, right? This is y equals the sine of x. So you plugged in different values for x and it spit out the y value. When you use the inverse sine, it's trying to do the opposite. It's saying, okay, I give you a y value and you have to tell me what the x value is. So if I say your y value is 1, right? So you could be an x value here, it could be an x value here, it could be an x value here, right? So there's multiple possible answers. And so the calculator basically restricts the inverse sine to kind of this zone. It says, all right, that's messy, sorry. When you ask for the inverse sine, I'm only going to give you an answer between negative 90 and positive 90. So it gets one of these nice clean things. You have to figure out whether it's that value, 180 minus that value over here, or whether or not it's that value itself, right? So it's kind of up to you as calculator operator beware. We realize that it's going to be obtuse, so in this case we can do 180 minus 36.9, and I'll prove it here with the calculator. If we take the sine of both these values, we should get the same thing, right? So if I go to my calculator and type in the sine of 36.9, oops, secret. So I come over here. Sorry, it's a little hard for you to see. So sine of 36.9, right? It gives me this thing. That should be the exact same value I get when I type in the sine of 143.1. So what is the sine of 143.1? Well, we can do that one too. 140, oops. Sine of 143.1. Nah. Maybe I'll just multiply it. What's it come out to? Yeah, okay, same thing. So those are the exact same value, right? So if I was to take the inverse sine of that answer, inverse sine of that answer, I get 36.9. It doesn't give that larger value of 143 to me because it's the inverse sine is, again, assuming you want an answer less than 90 degrees. So, so we have angle B2 and we have angle B1. Now, what are we missing? Let me clear this up. So we have this angle, boop. We have this angle, boop. We're still missing side C, right? C1 and C2. And we're missing angle C1 and angle C2. The next easiest one to get is going to be the angle. So to solve for the angle, we can do the triangle sum theorem. 36.9 plus 30, subtract that value from 180, gives you this one. And then same deal for C2. Plug and chug, you get 6.9 degrees for C2. And then finally, the only missing piece of information we have is side C. So we can use the law of sines to solve for side C. Again, we have all this other information. We have angle A, side A, angle C now. And we can plug these things in for both triangles. Plug and chug, switch it around. We don't have to do any inverses here. And we just get two different values for side C of 27.6 and 3.6. So this one asks as a hypothetical, what if we switch the values around? What if we say that AC is 18, the angle is 25 degrees, and side A is 21 inches? Well, 21 is going to be greater than this side B of 18 inches. So therefore we can look back to which one of these? Well, as it turns out, it's this one here, right? 21 is going to be greater than side B, and H there as well, but that should be a bit of a given. So Therefore, there's only one possible triangle, right? And we can go ahead and draw it, I guess, now that we know what it's going to look like. It's going to look like something like this, boop, right? Maybe not the most accurate, but that is 21 degrees, 21 inches. Now we can just use law of sines, right? We have an angle, a side, an angle, a side. I'm going to pause here, see if you can figure out what the values are for number 7. Cool. So hopefully use the law of sines to figure out the ratio of the sine of 25 over 21 is equal to, this is side B here, B. So hopefully you figured out what angle B was first, as 21.2. Once we have angle B, it should be pretty easy to calculate angle C using the angle addition postulate. Gives you 33.8. And then finally, when we have angle C, the very last piece of information we can get is side C using the law of sines again. So, oops, let me go that far. Side C coming out to 35.9 inches. So props if you were able to get all those. And good job using the law of sines. Cool, thanks. See you guys later.